So moving east, our final user presentation for today, we're moving over to, from Qatar, Hanif, is that great? Hanif is an Associate Director of Advanced Computing and also the Deputy CIO for Weill Cornell Medical College over in Qatar. He's responsible for an extensive range of HPC technologies from the cluster to the parallel file system, big data initiatives, and providing resources to the researchers who are doing the life sciences work. So if you would join us, please. I have to get my clicker. Get you all loaded up with equipment now.
I'm not so good at switching. I need this in the right hand.
Okay, we'll get you loaded for success. Excellent.
Thanks very much.
It should be your lapel actually that matters.
Yeah. Yeah, we hear you now. That's going to work.
Well, now, is that right?
That's good.
Okay. Thank you very much. This is actually my first supercomputing, my first time in NOLA, and my first time in a DDN event. So thank you for the opportunity and to join you. I'm not sure how all you are. It's been at least a couple hours since I remember this starting. So is there anyone from NOLA? Is it like a native New Orleans person?
Not one.
I was hoping for a kind of a saucy way of saying DDN, like DDN or something. Let me play this game anyway. So I'll say DD and you say oh. DD.
Oh.
DD.
Oh.
DD.
Oh.
All right. Better you than me. So just the maybe it's 5 o'clock. Let me tell you a little bit about Qatar and WCMCQ. I'd like to jump into technical stuff quickly, but since you probably haven't heard maybe that much about it. We are actually the Cornell Medical College in Qatar. It's the only medical school outside the United States that grants a U.S. degree. We have about 40 MDs graduate a year, and they all have 100% placement in residency within the U.S. So, it's actually a very successful program. We have like a $50 million research program, which is very successful as well. We have, again, I'm at the advanced computing there. What we have going on is a lot of research, a couple hundred researchers producing data. So this is the problem, right, or the challenge. And if I had, and again, there's probably a German in the room, so I won't try. But if I had an accent and I was like 6'6" and a little bigger, I might say that we have a problem. And I would say that if you want to live, come with me. So there are transistors which are going at Moore's law, but they're actually molecules that are going at a greater rate of increase and complexity than Moore's law. So we have more data coming out than keeping up with Moore's law will give us an ability to handle in terms of, let's say, just pure data points. And this is not just for biology, but it's certainly the case. And next generation sequencing is far outpacing any other data source. And so, of course, there are other people in the room who know about this. No secrets. This is a size issue. So genomic data that we have about 1,000 genomes worth of whole genome data. We have 1,000 exomes, which are 10% of an actual genome data set. What does it really look like? It's let's say it's about a terabyte off the sequencer, but actually when we really store it in a file system in any kind of long-term sense, what we thought, anyway, it's about 120 gig, 150 gig, and it happens to be compressed. And so if we actually uncompress it, it would be a lot bigger, about half a terabyte. There are about 1 billion objects in that genome file. And so if we wanted to do analytics on it, it would be a big data problem just for a genome. If we have 1,000 of them, it's 1 trillion tera objects. And so it's clearly a big data problem just in and of itself if we wanted to do analytics, but we can process it as an HPC problem. Often the first thing that happens is that the derived variance is what we want, which is what's the difference between this genome that I just sequenced, this person or the person with cancer. What are the things that are new in this genome information? So we call variance. That's a data reduction. We get about 5 gigabytes to 10 gigabytes per genome. 5 million features. So instead of a billion objects, maybe now, certainly a dimension reduction, but still a large data set. 500 million features in permanently interesting data. So that's what we have now, and it's going to scale 10 times in about 5 years. So exomes are similar to about 10%, but we're going to have 100,000 users at some point. So this is not even really analyzed data. This is sort of substrate for analysis. It takes HPC to get here, but a lot more analytics to go further to actually using that. So when we say genomic storage, there's actually DNA in the freezer which we have to store. And I think at some point, DDN is probably going to help us manage that data, probably on molecule. But until that point, we're going to manage it on storage in electronic systems. So the DNA sequence data, what we really mean by this object in the file is a read, which is the piece of sequence could fit into the sequencer. It comes out, we have data, we have the DNA code, quality information, coordinates of where each piece fits on what we call the genome, and all the variants. That's what we mean by data. And whole genome, as we said before, it's a lot of objects, and there's a compressed format. So, sort of fast forwarding to what is the HPC aspects of actually processing this data. I just kind of threw it up there. What's our usage? And this is typical, or maybe for an academic cluster, we get between 25 and 50% average usage on a weekly basis. So we're not topping out our CPU by any means. There could be a reason for that, but that's also not typical. Of course, our HPC storage was 65%. I gave you a slide, but it's at 85% now, and this 1.2 petabyte usable, which we're successfully using now for the last 18 months because of DDN. But that success is hitting a wall soon, so of course, we have to throw some money their way to help us get to the next level. So we're hoping to have 3 petabytes within 6 months to a year, but that's going to fill up. Of course, that's a challenge waiting for us at the other end of that acquisition. Acquisition of storage is not a solution to a problem. It's a solution to job security, and then the problem is actually analyzing data. So growth, 100% in the next 18 months, and I will just focus on this. This is actually the third graph at the bottom. I'm calling it network. It's what it is. It's within InfiniBand, the subnet, that's the cluster and storage, aggregate traffic, moving around between nodes and storage is 24 terabytes an hour. And that's actually not a lot for Texas big or even Indiana big. We only have actually 30 compute nodes. So these are normal multi-core nodes, but there's only 30 of them. They're not several hundred. So the amount of data that these cores are slinging around it within a compute hour is ridiculous. And just so I would say that the rise of that traffic is alarming, and we actually have we mentioned this a little earlier to the DDN folks that all this increased bandwidth and speed and better latencies, some ridiculous number that I saw up on a slide about 600 gigabytes a second. I don't understand that number, but there's a problem that's solving actually. So it's not just marketing and sort of we need to do more because we have to get some more technology. Actually, there's a latency for data. So data movement, just that 24 terabytes an hour in a tiny cluster is alarming. So data movement becomes our number one problem. Even that 85% usage is no longer really the technology issue. So the data network, everybody talks about shared HPC. So HPC resource has to access quickly this data, of course. But instrument to local storage is a big, huge issue. The terabytes are coming off the instrument. How is that getting on any system? How do we back that up? It's not clear that that's happening quickly. So we're installing it. Our first 10 gigabit switch to the lab. That's a big deal for them. They actually have more data initially, probably than we do. Local to shared storage. So of course, things that people generate, that's not such a big deal unless they have modeling in their workstation. Shared to desktop. I'm not sure if this is familiar, but biologists who know command line stuff are very dangerous people. It's seductive. Command line power is amazing, right? Linux, once you learn Linux, you never stop using it, and that's dangerous when they will grep, I kid you not, they will zgrep a 120 gigabyte file from their desktop.
Jeez.
And that doesn't happen twice, but they do try. Sometimes when they ask to mount that onto the desktop, we kind of ignore that for a couple of days. Anyway, so shared to backup is a fundamental issue that of course comes up all the time. But most of the time we're talking about Fabric, HPC. That is only one component for data. Data into cloud, everybody wants to do it. This is actually from Chris Stegdigian, a friend of mine who's a bio team founder. We have on the average for a normal family or cohort of genomes, probably around 20 terabytes in a usable set. Right? You don't use it, almost never analyze a genome at a time. So that half tera or something, it's not a computing unit. The unit of computation in terms of storage is about 20 terabytes plus. So if we get that data, often from PGI or somewhere, or we generate it, we still have to put it either into our HPC or if we put it in the cloud, it takes weeks to get that data into Amazon. Weeks, and that's from New York. I mean, we actually don't use Amazon. So if we mail it to New York and then ask them to load it, it takes weeks to get it to Amazon. So we don't do that. And then of course, then you check MD5 checksums, forget about the fact that we got data is the actual data we need. So it took 5 times longer to load data than it was to actually generate data. Not compute, just to load. So the sequencer is generating this idea of long tail. So we talked about size, about speed, and we're talking now about sort of a little bit more complicated issue of distribution of HPC jobs. So file patterns from the sequencer, the Illumina sequencer that we've become familiar with, there are actually 3 peaks, 3 modes in the file sizes for a sequencing run. It's not one kind of file, it's not one size, small, medium, large. Difficult to manage from a point of view of usage. So next-gen storage has to be high capacity, scalable, but also variable file types and usage for a single data set. Millions of files of 3 modes size, multi-protocol access, which of course now we think is becoming a standard issue. We currently write often in equal, not as asymmetric. What we want is we want a single namespace. It's when the biologist does the zgrep. He wants to be able to do it with all his files. And then the low ops effort, cost effectiveness, and some of the other chart options for upgrading. So these HPC use patterns. This comes from Glenn Lockwood's blog. He actually, it was about 5 days ago or about a week ago, he posted this on his blog. He's an HPC expert in next-gen sequencing from San Diego Supercomputing Center. This idea of the long tail of HPC, if you look, basically we get to 90% of jobs are within a cluster where there's 500 cores. So 80 to 90% of HPC jobs at San Diego are using less than 1,000, basically half, 500 cores. So it's a general purpose supercomputing center. San Diego has been around for a while, but until now, most of the jobs are long tail jobs. They're not thousands and thousands of cores. So, whatever the reason is, maybe it's just sort of small jobs. But then, if we look at file storage, it's another problem, right? Which is that most of the storage is small files, too. Again, this is not just genomics, but genomics mirrors it. So it's not just that we have, big users and then kind of the rest. We actually, most of our users are small jobs, small number of core users. And they're operating, unfortunately, on lots and lots of files. Which actually, from a genomic point, we didn't expect it. We thought our own files would be big. What they do is they, from their command line, uncompress that, or 20 gigabyte file in small pieces. Because that's the pipeline that they wrote by hand. So we didn't expect what happened, which is that they actually uncompress and chop everything up in order to process it. So one of our goals is to prevent command line access and put an analytics pipeline in place, but not have to replicate that, those hundreds of gigabytes of existing data into some kind of a triplicate object store. So still, there's some challenges, right? So a lot of things that DDN is doing. So these data patterns and I/O steps are being generated by this long tail. In his words, so-called 99% of science, right? Are not the 100,000 core jobs. DNA sequencing mirrors that. Parallel file systems may not always be that choice for every one of these things, even though parallel file systems work, but the usage is not exactly. And I think this is in Weill, what we're seeing is there are solutions. So that, again, it's just sort of where it is. An example of Luster that he points out, that the default struct size, of course, you're not going to use always the default, but the default struct size is bigger than Luster. And that's bigger than the, basically most of the files on that Luster file system. I'm not sure it doesn't work, but it may not be the best way of using Luster. Luster may not be the best format for that kind of file system. So what are some of the options? Well, first buffers fix everything. Frankly, it does. It's kind of hard to believe that it ends up being that what DDN sort of forward thinking is that all kinds of problems get solved by this intermediation of storage requests. Not storage, but storage requests. And this is an important kind of paradigm where high performance NAS is what actually Glenn recommends. The irony is what IME does to SFA or to what DDN is it turns, it's kind of like instead of being a fantastic SAN or a scale-out NAS, it's both, where it provides the storage request architecture that either or both can service at the same time. So of course, multi-core, right? Multi-threaded, many clients asking for the same or similar data is really what we're talking about. So DDN as a technology partner. There are other technology partners out there, frankly, not just price, but in terms of technical know-how and forward thinking, particularly application-oriented. This is one of the reasons why we chose DDN. Have SFA, it's fast, available, reliable, quick rebuilds. When things work, they work actually pretty quickly. InfiniBand was a requirement. GPFS is actually, Joel said, it's a great operating system. Of course, it's not the only, and it's not enough. We need something else, and so Performance Future, whether it's SFX now or IND later, we need something. Something is, so there's a reason why these products are coming, because there are legacies and high access to parallel acquisition. And I've been pushing with Laurent for some time now the idea of in-storage application. So IME, I actually just started to understand better. I mean, the folks at DDN were nice enough to explain now. IME is a solution to so many of our problems where it's storage issues, parallel or file size. But even what the architecture around me as a software solution means it's a general server. Just get a Linux server and install it. That Linux server can do something other than IME. And so we can actually do application-aware data APIs on the IME, so we don't actually have to do file descriptor-based computing on our remote nodes. We can just process data that IME provides in an application-aware way. And this is what we're trying to do. This is kind of my plug, so that DDN actually does it for us, for the genomics community, where you can get SAM tools on an appliance. And we just use the SAM tools API in a RESTful way so that we stop waiting for the data. We just use it. And IME is just the right way to go about doing this. And I'm sure this is the case in NCDF, all these ways. NCDF is the way it's stored. We can't change that, but we would love not to have to worry about it. And IME is a compute-oriented way of taking care of these things. In every, so you don't have to actually sell a genomics appliance. You sell a science appliance. Everybody can use the same thing. And I see that basically DDN's going that direction. And I'm excited to see it. Thank you for your time.
Thank you. Thank you.